Hi, I'm Namdar and I'll be presenting Levelset CNN, a deep variational method for instance segmentation. This is joint work with Yuan Xiang, Justin Liang, Wei-Chu Ma, and Raquel Urtasun. In this paper, we tackled the task of instance segmentation, which consists of detecting and categorizing the pixels of unique countable objects in an image. This task has many applications, for example, in autonomous driving for image simulation or scene flow, in medical imagery for segmenting the glands, and in robotic manipulation where the robot has to infer at a fine level the boundaries of each object. This is a very challenging task. For example, in the context of autonomous driving, a scene could contain many objects of varying scales and appearances. At the same time, many individual objects could have similar appearances and colors, making it hard to distinguish them. We could have shapes with thin structures, for example, the arm of this person. Also, there could be occlusion resulting in an object having many disconnected components. As such, this task requires models that can localize objects of varying scales and appearances, infer all their possibly disconnected components, and estimate for them precise boundaries. There are many works in the literature tackling this task. Most dominant modern deep learning approaches are generally categorized as either top-down or bottom-up. In a top-down approach, first, objects in an image are localized, and then their corresponding bounding boxes are segmented to foreground-background regions. Bottom-up approaches, on the other hand, typically perform instance segmentation by grouping the deep feature embeddings of individual instances without any early-stage object proposals. Before the success of deep learning in this task, variational methods were one popular approach for segmentation. For example, suppose we want to segment this car. A variational method formulates the problem as estimating the boundaries of the object. The boundary could either be formulated explicitly as a polygon or implicitly as the zero level set of a higher dimensional embedding function. Now, given an either explicit or implicit boundary parameterization, an initial contour is deformed through an energy minimization scheme so that at convergence it captures the boundaries of the object. During optimization, whereas explicit methods require heuristics to handle changes of topology, say in a multi-component object, implicit methods can naturally handle them without any heuristics. Recently, there have been deep resurrections of these older ideas, where either deep learning methods mimic the contour fitting process, or the optimization modules are directly combined with deep features in an end-to-end manner. Our proposed model falls in this category. In particular, we observe that most state-of-the-art top-down methods for instance segmentation are based on mask-CNN, which, while powerful and obtaining great results on public benchmarks, produces low-resolution masks within precise boundaries. On the other hand, classic variational methods produce structured outputs with desirable geometric criteria, but they rely on photometric data terms and hand-tuned hyperparameters that render them non-robust in practice. In our proposed model, we combine the best of both approaches. In particular, we obtain powerful feature representations for mask-CNN that are combined in an end-to-end manner with a variational method to obtain structured, precise boundaries. For the variational method, we employ the classic model of Chanvese. Chanvese is an implicit method where the boundaries are considered as the zero level set of an embedding function. A standard choice for the embedding function is the truncated signed distance, or TSDF, to the boundaries of the object. The TSDF is positive inside the object, negative outside, and zero on the boundaries. To perform segmentation, Chanvese minimizes an energy E, which is a function of the TSDF phi and two constants C1 and C2. The first term of E encourages the pixel intensities I of x to be close to a constant C1 in squared difference inside the object, which is obtained by first applying the heaviside function h to the TSDF phi to mask the inside, and then multiplying the heaviside with the squared difference. The integration is taken over the image domain omega, which is a subset of R2. Similarly, the second term encourages the pixel intensities outside the object to be close to a constant C2. Finally, the last term measures the boundary length and penalizes the boundaries which are very long. The effect of each term is regulated by the hyperparameters lambda1, lambda2, and mu. In short, this energy partitions the image to two regions where the pixels cluster together, while penalizing partitions that are highly irregular. In practice, these integrals are implemented as a summation since phi's are sampled at a discrete image grid. But we note that the space of phi's is continuous and uncountable. Now, how is the energy functional minimized to obtain the boundaries of the object? As a simple toy example, we binarize the car and apply the Chamvese optimization as follows. Suppose we have as initialization the TSTF to a circle. Optimization proceeds by first fixing phi and then updating C1 and C2, which turn out to be the average of pixel values inside and outside the object respectively. We show this with color circles in the third plot. Now, fixing C1 and C2, we can update phi using a gradient descent step. The gradient is obtained by differentiating the energy functional E with respect to phi. We can continue this procedure until convergence, as can be seen in the energy on the right. For this example, we see that at convergence, the zero level set of phi corresponds to the boundaries of the object. Moreover, C1 and C2 are equal to 1 and 0, the averages inside and outside. The steps involved in updating phi and C1, C2 are all differentiable. We'll unroll this optimization later as a recurrent network. Now we present our model where we combine mask-R CNN in an end-to-end manner with the Chamvese optimization. In particular, for each predicted instance in the image, we replace the masket of mask-R CNN to predict the following components. A TSTF to the boundaries, which will be used as an initialization in the Chamvese optimization. A deep feature tensor that will replace the image intensity values in the Chamvese energy functional. Image intensities are not robust and can vary in appearance within the objects, or could be very similar to the background, so we replace them with robust learned features. Finally, for each instance, we predict a set of hyperparameters. These parameters regulate the effect of each energy term and also the optimization schedule, for example by predicting the gradient descent step. After obtaining these three components, we unroll the Chamvese optimization as a recurrent net for a fixed number of time steps to obtain a final TSTF. At inference time, we can either simply apply the Heaviside function to the final TSTF to obtain a binary mask, or if we require subpixel accuracy, apply the marching squares algorithm to the TSTF. Learning of this model is performed jointly in an end-to-end manner. For the detection and classification heads, we use standard regression and cross-entropy loss. To learn the Chamvese components, we compare the final TSTF to the ground truth using a loss function, L of TSTF, which is the sum of L1 and binary cross-entropy. The gradient from this loss is backpropagated through the unroll optimization steps and through the initial TSTF head, the deep features head, and the hyperparameters head. This is the only supervision signal for learning the deep features and the adaptive hyperparameters. However, for the initial TSTF, we also apply the same loss in order to encourage it to be a TSTF. Our model obtains state-of-the-art results on the Cityscapes benchmark, where we improve the AP on the test set by 1.5. Comparing with mask-R CNN with the ResNet 50 backbone, we improve the AP on the validation sets of Cityscapes and Coco. Note that the boundaries on Coco are not always precise. As such, we take the model trained on Coco and evaluate it on Elvis, which has precise boundaries, showing AP improvements. Also, we see that the final TSTF improves the initial TSTF through the optimization. We also obtain more precise boundaries across different backbones compared to mask-R CNN, as measured by the average F1 between the ground truth and predicted boundaries. In this table, we see that by passing the gradient from the final TSTF through the initial TSTF head, we improve the AP of both. Finally, we see that the AP of the initial TSTF when passing gradients is higher than the AP of the final TS when not passing the gradient. This suggests that the Chamvese optimization can also be used only during training for improving the performance of the mask head and discarded during inference. Here is a video of our results on a cityscape held out sequence. Note that the predictions are per frame and not temporal. This is a very cluttered scene with many vehicles and pedestrians. We observe more precise boundaries throughout. In conclusion, in this work we propose Levelset CNN, which combines in an end-to-end manner the strengths of modern deep learning and the classic Chamvese Levelset segmentation, obtaining state-of-the-art results. Thank you for your time. Please drop into the QA session for any questions.